Today we are going to look at the knowledge area, electricity and magnetism. Now scientists believe that all magnetic phenomena results from forces between electrical charges in motion. So the magnetic phenomena results from electrical charges in motion. Now, a vast amount of energy is now being generated as a consequence of the relative motion between electrical conductors and magnetic fields. So what happens is electrical energy is transformed into mechanical energy. So for instance, our dishwasher, electrical energy is changed into mechanical energy. Washing machines, electrical energy is changed into mechanical energy. Vacuum cleaners, electrical energy is changed into mechanical energy. I can cite various instruments that converts or transforms electrical energy to mechanical energy. Even our instruments like the ammeter, the voltmeter, the galvanometer, all these change electrical energy into mechanical energy. And then these instruments are calibrated so that we can then read off the current on an ammeter or the voltage on a voltmeter. Now we're going to look at fields. We're going to look at the magnetic field, we're going to look at electric field, and we're going to look at the gravitational field. Firstly, we're going to look at the magnetic field and what the magnetic field is and how is it represented. We'll go through that. So, firstly, a magnetic field is a region of space where another magnet or ferromagnetic material will experience a force. And this is a non-contact force, right? The direction of the magnetic field by convention is chosen from north to south. I'll talk about that as we go along. And the path outlined by a freely rotating magnet is represented by a magnetic field line. Magnetic and non-magnetic material. Right, so we've got magnetic materials. They are essentially attracted by a magnet. Example, iron, steel are magnetized in the presence of a magnet. So they get attracted in a magnetic field. Material can be magnetized and attracted by a magnet are known as ferromagnetic materials. So a ferromagnetic material can contain at least one of these metals, right? Iron, nickel, and cobalt. It's useful to look at its position in the periodic table and see where they're situated. And then substances like copper, which is a metal, aluminium is a metal, indium is a metal, and nonmetals are not attracted by a magnet. Right. And these are known as non-magnetic materials. So copper, aluminium, indium are not attracted by a magnet, so they are regarded as not being magnetic substances. Let's look at a description of the field. Right, so we know that if we have a magnet and we bring another magnet near its vicinity, the magnet either gets repelled or attracted. That's, it's a fascinating phenomenon. Children love to play with magnets. But here we are interested in what is it that is actually making these or attracting these magnets or repelling these magnets. In order to understand a bit more about what's happening around the magnet, we need to have some idea about what a magnetic field is. So a magnetic field, right, is essentially a mental picture. Something happens in the region of the magnet, around the area of a magnetic field, right? So we use a magnetic field to describe a magnetic force distributed in space within and around and around something that's magnetic. So you have your magnet, and we are trying to establish or think about what is really happening around this particular magnet, right? So, and it's something that we cannot see, and we want to get a mental picture of this magnetic field. So, when we speak of a force due to a magnet, we know, for instance, when we thinking about a force due to a magnet, or for that matter any force, it has to be exerted on something. If there's a force, it has to be exerted on something, right? There has to be some interaction, and then you know that the force is there. So when we're dealing with a magnetic field, we can first look at a mathematical tool which we call a force vector field. I'll talk about this. It tells us the magnitude of the field, and it gives us the direction of the force on a small test particle at any point, right? So that's a vector field, and we'll talk about this as we go on, because a magnetic field is essentially a vector field. So is an electric field, it's also a vector field. So is a gravitational field, it's also a vector field, right? And what is a vector? I'll give you an indication of what a vector is as we go along. With the electric field, we use the electron as a small particle, right? There is no equivalent for this in a magnetic field, as we do not have magnetic monopoles. Now, as far as magnets are concerned, you always have a north pole and a south pole. You cannot have a north pole existing on its own and a south pole existing on its own. Unlike charges. Charges, you can have positive charges and negative charges, right? But when we're dealing with magnets always have two poles. Now, there are two ways in which a magnetic field can typically be represented. The first one is a vector field, and here the arrows show the direction, and that direction can be determined by a compass. And the magnitude of the force is given by the length of the arrow, right, in a region around the magnet. That's one way of representing it. But we're not going to use that picture or illustration. We're going to look at the magnetic field lines. Here we get rid of the vectors, right? And we connect the vectors in terms of lines. Right? But it's useful to have the vector picture so that you at least have an indication of the strength of the magnetic field. Now, we know we've got a field, we've got something around this a magnet, a bar magnet or a horseshoe magnet. We have some a region, the region around a magnet. There's something there which we don't really know, but we know it's exerting a force. And we want to get a picture of what is happening around this particular, around a particular magnet. So in order to get a sense of what's happening around a magnet and in that region, we can then visualize what's happening around it by using iron filings. Right? We have iron filings, and iron filings is a magnetic substance. And as we sprinkle iron filings around a magnet, we find that it gives us a certain pattern. And it gives us an indication of the field lines. There are no lines, but we then look at the pattern and we say we can represent what we see in terms of field lines. The iron filings, they act like tiny magnets, and the north and south poles align to the magnetic field of the bar magnet. Also, magnetic field lines are continuous, right? And what I mean by that is that they don't stop from the North Pole going to the South Pole, they are continuous. I'll show you this as we go on. And then there are imaginary lines, firstly, that form a loop. Right? They do not have a beginning or an end. Unlike an electric field, where you will find that the electric field lines they have a beginning and an end. Then these magnetic field lines are 3D lines, although we represent them as 2D, we represent them on a surface, right? And we represent the field lines by convention as going from the North Pole to the South Pole. That's by convention. That is arbitrary. Okay? And the lines do not cross each other since the field is directional. And lines, they concentrate more where field strength is strongest. Okay. Right, so this gives you a description of it, but now I am going to try and illustrate it by showing you what happens when iron filings are sprinkled around a bar magnet. Since we're dealing with magnetic fields in a SI system, a magnetic field is measured in terms of Tesla. Right, and it's named after Nikola Tesla. So I'm referring to the unit of magnetic field. Although we're not going to be doing much of that, what you're going to do in grade 11 and grade 12, you're going to deal with magnetic fields and its units. So I'm just giving you an indication of the unit in which it is measured. And the Tesla is essentially a measure of the force applied on a moving charge in the field. Right. Just to give you an idea here, a small refrigerator magnet produces a field of about 0.001 Tesla, and then the Earth's magnetic field is about 5 times 10 to the minus 5 Tesla, and that's more or less on the surface of the Earth. Right, now let's look at poles of permanent magnets, the aspect of attraction and repulsion, and the magnetic field. Right, now let's look at the pattern of iron filings around a bar magnet together with the associated field lines are illustrated as I go along. Let's look at this here. There you got a bar magnet, right? And you've got iron filings sprinkled around this bar magnet. When you look at it, you see, for instance, a pattern, right? And that's giving you some indication of what's happening around a bar magnet. Here at the South Pole, you see a lot of iron filings. Here at the North Pole, you see a lot of iron filings. And as we go further and further away, you find there aren't many, iron filings there. So by looking at this distribution of these iron filings and the density of it gives you an indication to an extent about the strength of the magnetic field. You say, okay, something is happening around this particular magnet, and when we have these iron filings sprinkled around the magnet, it gives us a certain pattern. And as you can see, there isn't, it's just giving us an indication of the pattern, but it's not giving us an indication of whether this is a line from north to south or south to the iron filings are aligned from north to south or south to north. We then create a schematic illustration so that we can then give an indication as to how these lines are actually moving and in which direction. So let's look at that and let's see how we illustrate it by using a vector field. Now, if you look at this here, we've got a north pole and a south pole, right? And then we've got magnets, compasses that are in the region of this particular magnetic field. And if you look at it, the compass gives you the direction of the magnetic field. So here you've got north, there you've got south. Look at this compass needle, how's it pointing? Look at this compass, this here, the south is towards the compass, towards the magnet, right? And if you look at this here, if you look at this and if you trace this, you'll see, okay, here in this case, you've got that vector showing you what the field strength is at that point, shows you what the field strength is at that point, and as you see here, this arrow is getting smaller, so it would imply that the field strength is less there, and it's less there and it's less there, so the length of the arrow is an indicative measure of the strength of the field, right? But also if we look at this and we try and track it and we say, all right, here you got a line going that way, here you've got there you have that here as you're going from north, you see there how your magnets are aligned and you're moving in that direction, and here from north in that direction. So arbitrarily we are now saying we calling the one pole the North Pole and the other pole the South Pole. I mean, either way, we could have called the North the South and the South the North. But here you've got these, and when I said lines or magnetic field lines are continuous, I meant that it goes through your particular magnet and it forms a loop like that. Right? It doesn't go from north to south and stops there. So for communication purpose, we say, right, these field lines move from north to south. And then your magnet aligns itself so that the south pole is where the north pole is, and the north pole is actually seeking the south pole. Right, so that gives you a vector diagram, right, which we could have used. But we prefer to use magnetic field lines, and that's how we represent it. So we got our field moving from north to south, moving from north to south, like that. And inside, surely that continues. Right. So what we do then, we have these arrows showing us in which direction the field is, and as you can see, it goes out from the north, right, and it comes into the south. Here it's coming, the field is towards the south pole. Right, and here what we have is we have these field lines, right, which has come out of that the iron filings that were sprinkled, right? And we don't want to clutter this magnetic field with a lot of lines, so we just have chosen a few field lines here. Then again, what other information does this field give us? For instance, where you see there's a lot of lines, say if I draw a square here and there's a lot of lines per square area, that would give us an indication that the field is strong. Here, if I have the same square area and there's fewer lines passing through that area, it would imply that the field is weak or weaker than the one near the pole. So the number of lines passing per unit area gives us an indicative measure of the strength of that particular magnetic field. And we want to know the strength of the magnetic field in different areas, because once we know the strength of the magnetic field in different regions of the magnets, then we have an indication of the force that will be exerted on a magnetic substance anywhere in that field. And when you go to grade 12, you will deal with magnetic fields and the forces that a magnet exerts on a particular magnetic substance in a specific region of the magnetic field. Here we have now field between a south and a north pole. Right? A south and a north pole. If you look at the pattern again, and we look at this region here, we're going to be looking at that region, right? A north and a south pole. And the field lines for that, here we have it. Okay? It gives us an indication again of the field lines moving from north to south. Here in the south it's moving towards the south. Here it's moving away from the north, and in between it's moving from north to south, right? And what you also need to remember is that these, whilst I've represented them here, they actually form loops, right? So when we have South Pole and North Pole, we find that they attract each other. Now let's look at two North Poles. Two North Poles, again, we look at this particular region and we find that, okay, we have these fields and there it seems like there's no field there, right? And obviously we could test it to see if a magnetic substance placed at that point is going to experience any type of force. Right? So again here, if I have a square area, I find the force is strong there, I find the force is strong there and there, because there's more lines per unit area, and if I put a magnetic substance there, we find that the force is not too strong, right? Right now, alignment of a compass in a magnetic field. Okay, so which would mean that, let's just do that. Right, in a magnetic field. So we're looking at the compass gives the direction of the field. Okay, we know that. It gives the direction of the field. It does not give the strength of the field. It just gives us in which direction is this particular field. Right? Now, in order to know what the strength of the field was or is, we need like a monopole or something, like something tiny. Right, but like I said, we don't get monopoles up to this stage. We haven't, nobody has recorded any findings related to a monopole. So we cannot use it to measure the strength of the magnetic field. Okay? So the magnetic field strength is actually determined by a charge moving through a magnetic field, but that falls outside the scope of this particular course at the moment. Right here, it shows you nicely that you've got your field, and your field then moves through your magnet like that, and it continues and it forms a loop. Right? And it shows you the alignment of your compass needles. There, I've illustrated this as well. Look at that, and we can obviously then say, okay, if I want to, I could say there's north, so I could go there, right? And I could go like that, and I could go, and then it comes like that, right? And here also we could say there, like that, and it gives us that direction. And here we could say it's going that way, and it's going that way, and here we got our arrow there, and our arrow there, right? And here it goes from north to south, and north to south, right? And here and there, right, we see that it comes in that way. Right, that gives us an indication of the field. Right, so let's look at an electric field. An electric field is a region in space where an electric charge experiences an electric force. Right. And electric field lines are from positive charge to negative charge. That's again by convention, right? We chose it to be like that. We could have used from negative to positive. And then the thing about an electric field, they are not continuous, right? Like a magnetic field. Okay, I'll show you what I mean by that. And you can get an isolated charge. That means you can get a positive charge, you can get an isolated negative charge. Unlike a magnetic field, you cannot get monopoles. That's either a north pole or a south pole on its own. They're always together, right? The lines in 3D, however, the lines are in 3D, but however we represent them in 2D, right? So we only use two coordinate axes, so we represent them on a surface, and that's sufficient for us for the type of calculations that we do. And again, the strength of the field is given by the number of lines per unit area. And another thing is lines of field do not cross. Now here I've given you an indication of an electric field line of a negative point charge, right? So see how it goes. It's concentric, and we're showing it also as being symmetrical. So the field lines are towards the negative charge, right? Towards the negative charge, and they converge. And again, the same story we have. If I want to know where the field is strong, if I take a square area here, I find maybe there's two lines going through there. If I use the same thing there, I find there's fewer lines going through that area, which indicates that the force here would be weak, right? And the force there on a charged particle would be strong. Right? Remember here we are now looking at the field between of charged particles, right? There's a positive charge. Here we have a positive charge, and here it's the same field, but here it moves outwards, right? Here it moves, or the field is moving outwards. So the electric field lines of a positive point charge, they move outwards, and they symmetrical. I've illustrated them there. Let's look at a positive and a negative charge here. Here again, the field lines move from positive to negative. Moves from positive to negative. But unlike a magnetic field, these lines are not continuous. What I mean by that is, for instance, it goes from positive to negative, but it doesn't go that way, right? It doesn't complete that particular loop. It stops at where the negative charge, positive charge is, right? So it's not continuous. And again, the same principle applies. If you want to know where the field is strong, and we say, okay, here it looks like the field is strong, there the field is strong, right, here in this area the field is maybe weak, here is relatively strong, isn't it? And here in between these charges, it also seems to be strong. Okay, so if we know if the field is strong and where it's strong and where it's weak, that gives us an indication of the force that will be exerted on a charge at those particular points. Now let's look at two positive charges. Two positive charges, we said, okay, the field goes out there. Same thing happens here. Right? And as we see that there between the charges here there seems to be no electrical field, and for instance here the electric fields is quite strong, right? So these are for two positive charges. If we had, for instance, two negative charges, the field would be the same. It would be the same, right? Only thing is, we would have had, so say if that was negative, right? Say that's negative, and say that's negative. What would it be? The same field, only thing is, the field would be towards there. Okay? Essentially the same thing. And the same thing here, right? Because we say it moves, the field moves towards, like that. Okay, so that would be two negative charges. Okay, there we have that. Right, now we come to a gravitational field. So we spoke about a magnetic field. Magnetic field is a region in which a magnetic substance experiences a force. An electric field is a field in which a charged particle experiences force. Now we come to a gravitational field, and the gravitational field is a space where mass will experience a gravitational force. Huh? Any object that has mass will experience a force in a gravitational field. Right? And any object that has mass obviously has its own field as well, right? Because of its mass. But let's look at the Earth. This is the Earth's gravitational field, and you can see the field lines are moving towards the Earth here, right? So if I, for instance, have an object here, that object will move towards the Earth. Okay? The object moves towards the Earth, and I mean, okay, does the Earth move towards the object? Yes, as well, but at this point, we're just looking at the Earth's gravitational field, and we find that the object moves towards the Earth and towards the center of the earth, right? So these field lines are directed towards the center of the earth. So if you have an object here, it will move towards the earth, there towards the earth. Wherever that object is moving towards the earth. You notice I'm saying towards the earth. I'm not saying it's moving down to the earth, because we don't know what is up and down. All we know is that the object moves towards the earth in relative terms. Right. So in these forces, the gravitational, the magnetic and the electrical forces are forces that act at a distance. That means these objects, or these the magnetic substance, or the charged particle, or the mass, they're not in direct contact with the entity. They are far away, and yet they are attracted to that particular entity. So that is why we call them forces acting at a distance. Right, so now we compare the magnetic field, the electric field, and the gravitational field, right? And what we do know is the magnetic, electrical, and the gravitational here, the magnetic, the gravitational, the electrical are considered to be non-contact forces, right? Non-contact, non right, non-contact forces. Okay, and they act from a distance, right? And as the object moves further away, the forces decrease. The forces decrease. Okay, the forces decrease. Okay, the forces decrease. Now let's look at the fields. We can look at the magnetic field, and we know it is a vector, right? Now I said I'll tell you what's a vector. What's a vector as opposed to a scalar? A vector quantity is a quantity that has magnitude and it has direction. A scalar quantity is a quantity that has magnitude and it doesn't have direction, right? So when we're talking about a vector and we're adding vectors, vectors can be added, but they have to be added in a special way, right? If, for instance, if I talk about a scalar quantity, and if I say 2 kilograms plus 3 kilograms is 5 kilograms, it's fine because mass is a scalar quantity. It's not a vector quantity. But if I'm dealing with a vector quantity like magnetic field, I can't say 3 Teslas plus 2 Teslas is 5 Teslas, right? Because when I'm adding this, I have to take direction into account. The same thing for an electric field. We need to take the direction into account and the magnitude into account. So we need to take the direction into account and uh, um, the direction as well as the magnitude. And even in a gravitational field, it's a vector. It's a vector quantity. Now, vectors is an important concept. I mean, addition of vectors. How do we add vectors? How do we subtract vectors? How do we multiply vectors? All these things, like what we're going to deal with. When we're dealing with when you deal with vectors, you will deal with how vectors are added and how vectors are subtracted, right? And we need to take the direction into account. Although we're just going to look at vector addition and subtraction in one dimension. Okay, this year, and then when you go to grade 12, you'll look at vectors being added in 2 dimensions. And then we also have, I had to tell you the type of force that exists, and it exists between a magnetic substance. Okay, here between a charged particle, and here between objects that have mass. Okay. Now, here we say I have a bar magnet that has a mass of 200 grams and I bring it near a magnetic substance with a mass of 200 grams close to it. What type of a force will exist between the objects? Right. So we say, okay, firstly, we know it is a magnetic substance, right? And we know that it has mass. Is this object got charge? No, I haven't referred to the charge at all here. So as far as we are concerned, because it's a magnetic substance and it's in a magnetic field, there will be a magnetic force. Right? There will be a magnetic force between the two. So there would be a magnetic force. Right. But these two objects also have mass. So if they have mass, there's going to be a gravitational force. Isn't that so? Yes. Right? Gravitational force. Is there an electric force or an electrostatic force there? No, because I haven't said, that these objects are charged. Right, so qualitatively, there's a magnetic force and there's a gravitational force. What is the magnitude of the magnetic force and gravitational force? That falls beyond the scope of the scores at the moment. But next year you will learn what the gravitational force is a function of. And one of the things you've already learned is that when the object is further away from the Earth, it would mean that the force is less. If the magnetic substance is further away in the magnetic field, the force would be less. So how is this magnetic and gravitational force related to distance? Qualitatively, the feeling we have is that as these objects in the respective fields get further from the field, then the force would be less. Right, but we don't want to quantify that relationship now. What force exists between a stationary proton and an electron, right? So I deliberately said stationary proton and electron. And what force exists between this? We know because a proton is charged and an electron is charged, we have an electric force. Right? And sometimes we refer to it as an electrostatic force, electric force. And we're going to be doing quite a bit about the electric force and charges in the subsequent lesson. But also we have a proton, although I haven't explicitly mentioned it, a proton has mass and an electron has mass. So there must be a gravitational force as well. Gravitational force. Right, there will be a gravitational force. Okay? Right, because it has mass. Now the point is, which force is stronger, electric or gravitational? Again, thus you will do in grade 11, right? Because you'll be given equations, but what you do know that the electric force becomes less as the charge is further away from an electric field, and we know that the gravitational force becomes less when the mass is further away from the object or further away from the Earth. Right, now let's look at the Earth's magnetic field now. The Earth's magnetic field, right, the Earth has its own magnetic field. How does this magnetic field arise? It's believed that it's because of the core of molten metal, right? And the Earth acts as a bar magnet. Right, and we know that the source of these fields are caused by moving charges. Right? So a moving charge causes a magnetic field. If the charge is stationary, it has only an electric or electrostatic field. So, magnetic north, right? It's a point where the magnetic field enters the Earth. And the magnetic north is constantly changing, right? Depending on the locations, because the activity in the core of the Earth is changing, so the magnetic north changes. And the magnetic north is actually found by using a compass. The geographic north. Okay, so there's the point in the northern hemisphere. I'm dealing a little bit with geography here. and where the rotational axis meets the Earth's surface, right? Where it meets the Earth's surface. And it is used in maps, right? And it is determined by the position of the sun. Okay? So let's look at this. Here we have the Earth. Okay? We know there's a North Pole, we know there's a South Pole, right? So where we have the Earth rotating in its own axis, so let me just maybe illustrate it like this. Let's say, no, maybe, right, say maybe, alright, let's stick to that. So here we got the Earth's axis going straight down like that, right? And here we have, for instance, this area here is then our magnetic north. Magnetic north, right? And there we have our geographic north. Geographic north. Okay. And then the angle between the geographic north and the magnetic north, this angle here, that angle there, whatever that angle is, let's say angle theta, that gives us the, I'll put it down here, that gives us the angle of declination. Give us the angle of, write it here, angle of declination, right, as the angle of declination. Okay, so when you're using your compass needle, here you see your compass, right, which direction is pointing, right, and it's actually seeking, it moves in the direction of the magnetic north or the geographic north, right? And when you use the compass gives you an indication of the magnetic north, and then the magnetic north and the geographic north may be like about 15 to 20 degrees. There may be a difference, so sometimes when you're using your compass you have to then account for the angle of declination, otherwise you find yourself 100 or 200 kilometers from where you actually have to be. Right, now let's look at the importance of the Earth's magnetic field. Right? It is the area above the Earth's magnetic field is known as a magnetosphere. And the magnetosphere plays an important role in life on Earth, right? Yeah. So the magnetosphere, what it does, it deflects winds from the Earth and prevents it from reaching the Earth, right? And what happens is solar winds. They are radioactive and they come from the sun, right? And these are highly charged particles with a lot of energy. And it results because of the reactions in the sun. So telecommunication systems and life would be non-existent. Okay, would be non-existent if the Earth's magnetic field did not form a protective layer. Alright, now let's look at this. Here you got solar winds from the sun coming, and here you have your magnetic field, right? Your magnetic field. Now what happens, these solar winds, they high energy particles that move through the air, right? It could be charged particles, it could be alpha particles, it could be electrons, and as these particles move, they move, and what happens is they then deflected by the Earth's magnetic field. They get deflected in the Earth's magnetic field, right? And they go past there. So we find that they move and they are prevented from coming into the Earth. But sometimes what happens is that you may have these solar winds. Actually, some of them, if they don't escape, they come and they spiral into the north pole of the Earth, and the same thing can also happen here at the south pole, right? It can spiral in there and go towards the south pole. So we have these solar winds that are moving towards the Earth, and they strike the atmosphere here in this area, right? They hit the atmosphere, they strike the atmosphere there, and the same thing here, strikes the atmosphere. There. And so, firstly, we find that happening, but sometimes what also happens, some of these solar winds, they escape and they are then captured within the magnetic field of the Earth here, and we find that they form belts of radiation, and these are highly charged particles that are within the magnetic field there, and they captured, and we call them radiation belts, and it's normally named after a person called Van Allen, right? He is a person that discovered these radiation belts. And what happens with these radiation belts now, like they're highly charged, and when you have a satellite in the vicinity of these radiation belts, they can cause a lot of interference, right? So they can be a nuisance in a way. All right, so getting back to this aspect of where these solar winds are then spiral at the North Pole here or the South Pole there, what happens is that it hits the atmosphere and then it strikes the atmosphere, and when it strikes the atmosphere, we get these auroras, right? The aurora borealis and the aurora australis. Here we go. Right, so we have here, so the magnetosphere deflects most of the solar winds, right? So sometimes the sun is very active and we have a large concentration of charge that enters the atmosphere. Okay? And these charged particles, they collide with air particles like oxygen and nitrogen. These high energy particles collide with air that's made up of nitrogen and oxygen, and there can be a whole lot of other elements as well in the atmosphere there. So what happens is we find that beautiful color glow at the poles, right? And the glow in the northern hemisphere is known as the Polar Borealis. Now, just to give you some indication of how this particular light is emitted. So let's say, for instance, that we're talking of nitrogen. So we know what do we know about nitrogen? We know nitrogen has an atomic number 7 and a mass 14, right? And we know that if we have, for instance, if we have to represent the electronic configuration, is 1s2, we know is 2s2 and 2p3, right? And if we look at this, and if I have to represent it, I say, all right, we've got, using our shell model, that's our nucleus, we got one shell, then we got two shells, and then we got three shells like that, am I right? And then in the first shell, we've got 2 electrons, and then there we have 5 electrons, say 5 electrons like that. Right, and what we do know is when electrons move from a low energy level to a higher energy level. So let's say it moves up from, that's in the ground state, right? So when the electrons move from a low energy level to a higher energy level, it absorbs energy. Right? That's a basic principle. And it gets to be in an excited state. So when it moves from low energy, okay, so when it moves from low energy, okay, when it moves from low energy to high energy here, it moves from a lower shell to a higher shell, it absorbs energy. Okay? And when it moves from a higher shell to a lower shell like that, it releases energy. Right, it releases energy. It releases energy. Okay, it releases energy, or it emits energy. So once you have the solar winds hitting these atoms, I'm just using nitrogen as an example, hitting these atoms, the electrons in the outermost shell are excited and they go into higher energy states. But then they quickly fall to a lower energy state, and when they fall into a lower energy state, it releases energy, and that energy that it releases, and we did this, E is equal to hf. The energy of the photon is dependent on the frequency, and if it emits a color of a certain frequency, if it emits a certain frequency, that frequency is related to its color, and then we see this beautiful aurora here where the electrons are first excited and they move from higher energy levels to lower energy levels, and in doing so they release energy, and that is the light that we see because they release energy in the visible spectrum. And now let's briefly look at the theory of magnetism, right, which is not examinable, but we'll just go through it quickly. So when a bar magnet is broken, every piece becomes a bar magnet, right? Like I said, you cannot take a bar magnet, break it in half, and then get a monopole, right? There's no monopoles. The smaller pieces also have a north and south pole, right? And the smallest magnet is inside the atom, right? So when an electron in an atom moves, it causes a small magnetic field, right? We haven't dealt with this. We've dealt mostly with the electrostatic field when we were dealing with the atoms. Right. Non-magnetic substances, the fields are random. Like here, the field is random. Okay? Because you don't have a magnetic field, the domains are random, they pointing in all different directions. In a ferromagnetic substance, the fields are grouped and they are aligned to a specific direction. So if I have a field here, and you see that tells me a magnetic field, right? There's a symbol for magnetic field. And the domains, so if my field is going upwards, I find that all these the domains are then aligned here. See, all are aligned and they all in the same direction. Right? That's when a ferromagnetic substance is in a magnetic field. Right, now let's look at an exercise. Define the term magnetic field. Right, so what's magnetic field? It's the region right, in space in which a magnetic substance experience a force. Yes, a magnetic substance will experience a force. If it's a stationary charge in a magnetic field, it's not going to experience a force. A stationary charge experiences a force in an electric field. So write down the properties of the magnetic field lines. What do we know about it? We said they're continuous, right? That means there's no end. It forms a loop. We could say they run from north to south, and that's by convention we chose it to be that. They do not cross each other right, since the vectors, and where lines are more concentrated the lines are more concentrated where the field is strongest. Right. Then we go to which magnetic pole of the Earth will the north pole of a compass point to the north magnetic pole. Okay. Magnetic pole. So give an example of a phenomena that are affected by the Earth's magnetic field. We know we got the Aurora Borealis, and that's like the northern lights. And that also happens in the southern hemisphere, and there we call it Aurora Australis. Right. And then what else? Solar winds, right? We got solar winds. Solar winds, and what do solar winds? The magnetic sphere deflects solar winds, right? And the magnetic sphere or magnetosphere deflects solar winds. Okay, and it prevents, and what it does, it then prevents electrical damage. Right, imagine, I mean, all our electrical electrical lines, and if we had these solar winds moving past them, and we know that these solar winds are highly charged and they have magnetic fields, and that will mess up our satellite systems and a huge range of electrical apparatus. Right, and then what is the distinguishing property of a ferromagnetic material? Right, ferromagnetic materials are substances that are strongly attracted by a magnet. Okay. What three metals are the most important ferromagnetic materials? It's iron, cobalt. Right, I'll write this out in full. Cobalt and nickel. Right? And like I intimated earlier, also check where the position is in the periodic table. Right? And then what special alloy is used to make very strong magnets? Right? The alloy is nickel, right? Which means aluminium, nickel, and cobalt, right? They can form very strong magnets. And you know, I had spoken earlier that aluminium is not a magnetic substance, right? But yet, when it's in an alloy, this alloy forms a magnetic substance, and it can make strong magnets. What is a non-magnetic material? So it's a material that is not affected by a magnetic field. Under what circumstances will a magnetic force be one of repulsion and one of attraction, right? So of repulsion, so say repulsion between two dissimilar poles. Okay, that means a north and a south, or a south and a north, but repulsion between two similar poles, between two north poles, or between two south poles. And then what determines the field intensity at any point in a magnetic field? We normally say it is the number of lines, right, passing per unit area. Right, sometimes we also refer to it as a, you'll hear this term in grade 12, say the flux density. Right, there you have it. We're done, and see you the next time.